So the first thing that we want to discuss today is the actual overall global positioning or GPS system. So uh, what it actually is a constellation of satellites and ground stations uh, around the Earth. And basically, we use these to be able to actually do the positioning. So there's a several satellites. They're in an orbit. So they take about 12 hours, so 2 orbits a day to complete an orbit. And there's basically like 6 different orbits. And the idea is that basically, no matter where you are on Earth, you should have line of sight to 6 of those satellites at any time. And that is going to allow somebody with a GPS device to determine their position by looking at the signals from those multiple satellites. Right, so there are currently 31 of these satellites in the constellation. And like you said, basically they're in one of 6 orbital planes. So if you take the circle that the satellite makes in an orbit, you can then make a plane that circle lies on, right? That's all that means. And it takes, 12 hours, so you do 2 orbits a day. So they are roughly 20,000 kilometers above the surface of the Earth. And there was an expansion, basically introducing additional constellation or additional groups into the constellation. And so this is just on the right there is just sort of a cartoon picture of how the satellites orbit around the Earth. And again, the idea is being that you can always see multiple satellites. So, I think it's fairly obvious how useful it is now, but this GPS took a lot of money and time to develop, right? And it's not something that was really going to be developed by a commercial company, at least originally. So obviously, it was developed by the military for their purposes, right? So during World War II and the Cold War, it became obvious that you need navigation systems for aircraft, for ships, for guiding missiles. So militaries began to develop these navigation systems. And there was a few things that were developed prior to the existing GPS system. LORAN, Decca, Sputnik was apparently part of a navigation system originally. Transmit, SACOR, these are all acronyms, obviously. But basically, they're just different navigation systems. But like I said, development of all of these systems was developed for military applications by, in the U.S., the the Department of Defense. And the idea is, if you need to know where a ship or an aircraft is, you want one of these navigation systems. And then also, if you're firing, missiles, ICBMs, that sort of thing, you want to be able to position all of your military hardware. So in 1973, the project was started. As we said, it was created and owned by the U.S. government. Specifically, the Air Force is the branch of the military that's in charge of it. So this was during the Cold War. So there was, arms race. There's a lot of money going into defense research at the time. And so there was both the justification, the money, and the desire to research, develop, and deploy this constellation of navigational satellites. Some specific things are, if you have a ballistic missile submarine like the U.S. does and did, you want to be able to accurately tell where you're firing from so that you can fire accurately. And then also, again, intercontinental ballistic missiles and bombers are all, so these are all large strategic goals of the US military. So they're justified for being able to spend a lot of money. So you had, a number of people working on it, principally Roger Easton, Ivan Getting, and Bradford Parkinson at NRL, which is the Naval Research Lab, Aerospace Corporation, and APL is the Applied Physics Laboratory that still exists and still works with NASA. So in 1978, the first satellites were actually launched. And by 1995, you had a full constellation of satellites in orbit. So basically, in the 90s is when you start to see civilian availability of GPS. And so one thing is, if you're just driving your car, you don't need the level of accuracy that a missile does, if you're just trying to find yourself on a map. So initially there was basically a reduced accuracy for civilians, which was ended in May 1990. And, according to their stated policy, they don't intend to go back to that. There are a number of restrictions on the capabilities that civilian GPS receivers have. The idea being that you basically don't want anybody to be able to go and buy a complete missile guidance system at Radio Shack or Best Buy. So usually the limitations are on some combination of altitude and speed, right? So basically, if you have a satellite or a receiver that will operate above 18 kilometers, well, it cannot operate above 500 meters a second without requiring special licenses. And again, this is the idea being that, well, if you're a civilian, you really don't need these, except, in a few cases, maybe like aircraft, commercial aircraft guidance, sort of thing. But the idea being that if your receiver exceeds these, it'll basically turn itself off and stop giving positioning information if it exceeds those limits. And by having that sort of limitation, you can now classify that receiver as not part of a weapons system. So you can export it, you can manufacture it. So obviously, other countries do not want to be dependent upon the United States for their own navigation. That doesn't mean they don't use it, but obviously if they, especially if they're a country that may not have the best relationship with the US, they don't want to be dependent on the US system. So you have a number of different systems developed by different entities. There's a Russian system called GLONASS. The Europeans version is the EU version is called Galileo. China's got one called Baidu. Um, Japan has one called QZAA, which is an acronym standing for Quasi-Zenith Satellite System. And then India has their own one, navigation with the Indian constellation. So, you know, like I said, these satellites are pretty expensive. So you can see, especially with some of the countries that are have better relations with the U.S., they as of the dates listed here, they haven't spent a lot of money to put additional satellites into orbit. Additionally, a lot of your GPS devices are capable of working with multiples of these systems. That gives you redundancy. It allows you to do cross checks and get better and more quick fixes of your position. But how do you actually determine the position of your using the GPS signal? Well, you use a technique called trilateration. And the idea is basically, is being able to determine the distance from at least 3 satellites at the same time. And if I know where those satellites are, I can then triangulate my position. So basically, the GPS satellites broadcast their position and a very accurate timestamp. And what you receive on a GPS is you get the satellite's position and you get their timestamp. But I can then tell how far I am away from the different satellites, because if I have multiple satellites that broadcast that time signal to me, I can then see when I got those signals from the different satellites and tell how far away they are. Right. And since these are radio signals, they are electromagnetic radiation. So it will take, based on the speed of light, a certain amount of time for that signal to travel from the satellite to your receiver. And it's fairly simple. The distance is just the speed of light times the difference between when you received the signal and when it was transmitted. It's just distances, speed times time. So, doing that, you basically get a distance from each one of these satellites. And so the way it's drawn here is you get a circle, but in reality, this is 3-dimensional. So you get a sphere around each one of these satellites based on how far you are away from them. And then since you're getting this from multiple different satellites, you then just look at where those spheres intersect, or the circles in this 2-dimensional picture. And by looking at that intersection, you can tell where you were. So as you can see here, basically you would know how far you were from satellite 1. So you could be anywhere on that circle. Well, now when we combine that with a second satellite, I have to be somewhere on this circle and this circle. So that means I could be here or I could be here. And then when I combine it with a third satellite, it narrows it down to this single position right here. So like I said, in reality, you're getting spheres because it's a 3-dimensional object. It's a 3-dimensional world. And so the intersection of all the spheres is what gives you the point. But if you take three spheres and you sort of overlap each other, as you can see up here, there's actually two different points, right? With the circle, the two-dimensional circles, you only needed three. But as you can see here, if I take three arbitrary spheres, I'll actually have 2 points, which means I will need a fourth satellite to narrow it down between this point here and this point here. So that's why you usually talk about having a fix from 4 different satellites. And that's what you need to be able to tell, both your position on the surface of the Earth and the altitude. So just to summarize over that, you get a time and location from a bunch of different satellites. That allows you to calculate how far the time allows you to how to calculate how far you are from each of those satellites. And combining that with the position gives you a bunch of spheres that you could possibly be in. And then by looking at the overlaps between those, we can find their position. For a lot of things, you don't really care too much about the altitude, because if you're in a car, right, you're on the surface of the Earth. That's not a particularly interesting quantity to know the altitude. Or even if you're just going up, somewhere in the range of 100 feet or 1,000 feet, that change in elevation is small compared to the distance from the satellites. So you're effectively on a flat surface. So that means for a lot of those cases, you only need 3 satellites. And because that just gives you the position on the surface of the Earth, that's called a 2D fix. And with a fourth satellite, then you can get the full position of latitude, longitude, and altitude. However, this is not a perfect system. There's always uncertainties. There's always errors, as we talked about. So the timing signals on the GPS satellites is very, very accurate. Okay, it uses a atomic clock, and it is basically some of the most accurate time measurements that we have invented ever. So there are clock errors, but it's fairly small. More importantly, there is actually fluctuations in the speed of light through the atmosphere, depending upon like the density and the temperature and the pressure. There is a certain amount of actual geometry and physical size involved with these satellites. They are not infinitesimal points. Signals can be blocked, especially if you're inside a building, is the most obvious example, right? You may not be able to get a GPS position because you're inside and the building is blocking the radio signal. But that can also happen with mountains and to a certain extent stuff in the atmosphere, but not very often. And then obviously you can have a broad range of quality in the receiver that you're using to actually receive those signals, and how quickly and how accurately it can do the calculations. So sort of your standard GPS that's in your phone, the idea is they're accurate within about 5 meters. However, when you start to get close to large objects, especially buildings, that can get worse. because you can start to get reflections off of like the side of a building, and you could be blocking a number of the satellites. And then obviously, if you spend a lot of money on a very nice GPS receiver, it can be very accurate, but there's probably going to be limitations to it just for the same sort of thing with that, the altitude and speed limitations. So just to discuss these errors, right? The clock errors, you have a you have two clocks, right? Because you have the time that the signal was transmitted, which comes from the satellite, and the time that the receiver saw the signal. So obviously the satellites are very accurate. They're going to be more accurate than your small little receiver. They use an atomic clock, so they're using a decay of an isotope to measure time. So they're very accurate, but they can also drift as over the course of time, right? If the clock is running slightly slow or slightly fast, that sort of error is going to accumulate. So that has to be corrected, and that's partially why you have ground stations, so that you can then make corrections to these clock signals. Obviously, the much less accurate clock is the clock that is in your GPS receiver, because it's not a several billion-dollar GPS satellite. It probably will just have a simple quartz oscillator clock. So nothing fundamentally different from like a $10 digital watch. So this is going to be what is probably the largest source of your error, but there are a few tricks you can do by basically looking at the signals from multiple satellites, so that you can do a check on your receiver clock. Like I said, the atmosphere can actually cause changes in speed and direction of the signal. So mostly the signal travels in a straight line and at close to the speed of light in vacuum. However, because you have such you need such accuracy in the timing, very small changes can cause errors. So depending on what it's actually traveling through, the speed can change, and also the signal can be bent slightly, as it transmits through. Most importantly, the part of the atmosphere called the ionosphere, which can actually be electrically charged. So these errors are dependent on how far it goes. The signal has to travel through the atmosphere to get to you. So if the satellite is directly above you, that's sort of your best case scenario. It has to travel the shortest amount of distance through the atmosphere. Whereas if it's a satellite that's, very close to the horizon, it's coming at a much flatter angle. So it would have to come through like this. So it's going to have to travel through a lot more atmosphere. So there's more space that it can be affected by. So like I mentioned, specifically, the part of the atmosphere that can affect it the most is called the ionosphere. And basically, the signal can bounce around a little bit. which can give you delays or bend the signal. So the picture here is a very, very exaggerated view of what it would actually look like. Basically, it would look like a straight line to your eye if you could see it. But as I said, you're required such specific timing. Very small changes can cause you to have an error. So one thing you can do is with those monitoring stations is basically you can model the ionosphere and then you can transmit corrections out that the receivers can view and receive, and that allows you to minimize or reduce that error somewhat. Also, usually with signals like this, there is a bit of a frequency dependence, as in the changes for a higher frequency radio wave could be larger than a smaller frequency. So you can basically transmit over multiple frequency bands and compare them and reduce that error. The another part of the atmosphere where there's actual weather and clouds and stuff like that is called the troposphere. And here, your changes in pressure and density and can cause errors. Usually, this is not a frequency dependent. And there's, depending on the different gases in the atmosphere, you can get different effects. Specifically, there's basically the effect caused by all of the dry gases, which is basically ideal gas law stuff. It just is due to temperature and pressure. And then there is the difference due to water vapor. And, if there's clouds there between you and the satellite, that can end up adding up to a lot of water. But, there's a lot of variation in the humidity and the amount of water vapor between you and one of the satellites. So that's harder. That has a lot of variation and is harder to predict and model and correct for. So another thing is basically when you have error, so you have a slight thickness to your circles or shells, depending on how they intersect with each other, you're going to get different effects, different changes in your error. So part A here is sort of like the ideal case if you had perfect circles with no thickness. But once you consider the other sources of error, well, in each of your circles or your spheres, now they're, instead of being a line, they're like a little shell with some thickness. And depending on how they line up, you get a larger or smaller uncertainty. So if they're basically crossing each other kind of perpendicularly, well, I still know I'm in this green region right here. So there's a relatively small error. But if they're sort of lined up next to each other, so they're just kind of touching each other, well, now that thickness effect has a much larger uncertainty just because of the geometry of the two spheres that I'm trying to intersect with each other. So here you can see there's this much larger broad region where you could be in. and that's just that is called uh, geometric dilution of precision. And basically, if all of the satellites you can see are close to each other, that means the uh, uh, uncertainty in your position due to those other errors, the clock error and the atmospheric error, is going to be much worse. And then finally, you can just have stuff be in the way. Uh, like we said, GPS uses radio signals, um, which can pass through, a certain amount of material. But if you have a lot of uh, uh, material, or if you have some nice metal, that's going to either block or reflect the signal. And I mean, I think everyone has seen this. If they're in their house, there may be parts of their house where they can get a GPS signal, and parts that they can't. Especially if you're near a window. In particular, here on campus in LSU, we work on the third floor, and there's a partial fourth floor above us. So if we are underneath the parts of the building that have that fourth floor, we can't really get a GPS. But if we go to parts of the building where there's basically just the roof above us, we can usually get a GPS signal. Additionally, signals can bounce off of buildings and other solid objects. And what that means is you can get a signal, but it will have to travel through a longer path. So you can see here the straight line distance from the person to the GPS satellite is blocked by this signal, but they are getting this reflected signal, which is giving them a bit of an inaccurate reading in the distance. But the thing you got to remember is basically this distance from the building that reflects the signal to the person is actually really small compared to the 20,000 kilometers that satellite is. And then obviously there's other sorts of interference. There's radio wave interference. It probably isn't somebody purposely transmitting, but there's a number of natural phenomena that can basically put out a bunch of electromagnetic noise. So like lightning storms, if you have a bunch of ionized particles in the atmosphere from some sort of solar flare or solar event, that can cause you to have a lot of interference. And then obviously every once in a while they have to do maintenance on these satellites, so they may need to shut it down to do something for it. But the biggest thing that probably is controlling your accuracy is your receiver, because it's the difference between a $10 GPS, $30 GPS receiver is not going to have a lot of engineering trying to make it work right compared to the multi-billion-dollar GPS satellites. So, a lot of the things we suggested was, hey, you can use multiple frequencies. Well, that means you have to engineer and you have to pay for your receiver to be able to do that. And military receivers obviously you usually care much more about position accuracy and reliability than cost. So you're going to have a multiple frequency receiver. For civilians, it's usually not that big of a deal if you temporarily lose GPS. So you go with the cheaper option, which is a single frequency receiver, which is not to say that they don't exist. It's you just have to pay for it, and it's usually not worth the excess cost for most people. So, just to reiterate and summarize, you have, you know, the four different types of error. You've got clock error, atmospheric error, the geometry error, which is due to the way that your circles overlap, and then you can block or reflect the signals. Um, and as we talked about as we went through, there's mitigation methods that are used. Uh, Basically, you have a monitoring station that is trying to do some sort of modeling and correction, and it's going to send those corrections out. So additionally, you can basically improve your positioning and navigation through some sort of separate system that you use to augment your GPS. So one of which is called the WAAS. It is a system maintained by the FAA, and it is, you know, it's basically used to give aircraft better positioning. So obviously, if you lose position in an airplane, that's a much bigger deal than losing position for a car on the road. So you need that higher reliability. Another system is called CORS. It's run by NOAA, the National Oceanic and Atmospheric Administration. And it's basically a archive of the GPS data. Additionally, there's a few other. There's something called the GDPS. It's a augmentation system used for NASA missions. And then there's a basically an international system of monitoring stations called the GNSS, and those are going to include those sort of corrections that we talked about. So in particular, how that differential GPS correction works is you have a base station that you know where it is, and you are looking at what the GPS signals are, and you're transmitting a correction to your receivers. So you have your GPS signals up, satellites up here. They're not only transmitting to this person with the receiver, who could be anywhere, but your ground station is monitoring that. It knows where these satellites are, and it knows where it is because it's in a fixed location. So it can then correct for like those small timing errors, and send those corrections out to people, and give you a much more accurate location, you know, down to the centimeter level. Most of us don't need that, but it can be useful for things like surveying. But that's sort of how the system works, but let's talk about how to use it. So what does the GPS actually give you? It gives you a location. It tells you where you are. It can help you navigate, tell you where you're going. You can track stuff, i.e. you have something that's automated out there with a GPS receiver, and it's telling you its position. You can use the GPS system to map and do surveys. And one thing in particular that can be useful is you can use it to basically give you a standardized clock tick, allowing you to synchronize stuff that is distant from each other. Uh, so the signals that the satellites send out are encoded a specific way for the receivers. This format is called a NEMA sentence. It stands for National Marine Electronics Association. And there's actually a few different types of NEMA sentences. And all these are just standardized character strings separated by commas that have different pieces of information in each one. So some of the ones that you may run into, there is the RMC, and each one of these groups is called a sentence. So this is an RMC sentence, a GGA sentence, and so each of these has a name, and they have a set of specific information in them. So, for example, the RMC is called that because it's the recommended minimum. It has the time, a status number, which is sort of telling you how good your fix is, your latitude, your longitude. It's going to give you a speed, so how fast you're going, what direction you're going, and then some other data and some magnetic magnetic field information. So there's a whole bunch of different ones of these, and it sort of depends on your application which one you need. For our usage, RMC and GGA are what we use a lot of the time, specifically because we're looking for altitude, longitude, and latitude. So you'll notice in particularly the RMC does not include altitude, whereas the GGA does. So this is what one of these sentences looks like. Well, this is what you'll see if you go look it up. When you get the actual sentence from the GPS receiver, it's not going to have HHMMSS. It'll have the hours, the minutes, and the seconds. So each one of these sets of characters actually stands for the information that you're going to be getting. So the first thing, you always have this $sign, and then you always have a preamble that tells you what it is. So this is a GPS GGA sentence. So that's why it has this GP GGA. So then the next thing you get is a time. You get a latitude in this specific format. And this is the direction, right? Because this will be 0 to 90 degrees, but you don't know if it's north or south. So there will be an N or an S telling you which way. You will then get out to 2 decimal longitude, and again, it'll be east or west. You'll get this fixed quality number, and basically it tells you, hey, do I have no fix? Do I have a GPS fix? Do I have a better GPS fix? I mean, you can sort of look at what all of these are if you're interested. It will tell you how many satellites you can see. It'll give you a number of this horizontal dilution of position. That's related to that geometric error that we talked about. So that's sort of depending on where the satellites that you're looking at, how inaccurate is your position because of that. You'll get an altitude, a unit, and so this geoid and WGS 80 ellipsoid, those are just models for the shape of the Earth, right? The Earth is not actually a perfect sphere. So what you want to know, you can basically model the shape of the Earth as something that's slightly fatter around the equator, and these are the two shapes that you can use. And you, instead of an altitude above the sphere, you can do an altitude above this shape. And then there's a time since last update. And then finally, the very last thing is a checksum that is a number that's used to verify all of these previous values. Again, this is just a example of a different sentence. This is an RMC, and you'll see the format is different. So for each one of these, each one of the different sentences, you can look up the equivalent, this is what the information in that sentence is, and this is how it will be encoded. So in particular, if you go to the website, there is under this unit, which is unit 14. So if I bring up the LACES website, and I go to the GPS unit here, there is a NEMA reference document, and this is going to have all the different strings and have that formatting information for you, which is a useful reference to have.